sorry that the room is so big. This is a good turnout. Oh, yeah. Our first year doctoral students are over there. Yeah. How do you meet?
Oh, good. Yeah, intense. Everyone, I could have used more time. Oh, that's great.
Yeah, I can't wait to. I'll have to find a time to debrief with you about that.
Yeah, fascinating.
Okay, well, it's a real pleasure to have Jeanne Vandriesen here with us today. But before I introduce Jeanne, I want to just give a quick shout out. Our coffee today is supplied by BYO, our very own BYO. So thank you, BYO. And the cookies are from Whole G, our local bakery. So there are still cookies left. So yes, run up and grab a cookie. That's right. That's the way. That's the FES way. So it is a real pleasure to have Jeanne Vandriesen here with us today. I asked her how to pronounce her title because I would have totally botched it. She's the Duquesne Light Company Professor of Civil and Environmental Engineering. She's also the Director for the Center for Water Quality and Urban Environmental Systems at Carnegie Mellon University. I met Jeanne, I think it was about 10 years ago. We were in a leadership communications training program to get together, and one of the things that struck me, I think it was about 10 years ago, was one, how smart she was, and B, how articulate she was, and C, how inspiring she was. And so it's really a pleasure to have her here today to talk a little bit about her research. If you look at her CV, you'll know right away that she's an incredibly busy person. She serves on a number of boards and panels. Currently, she's on the EPA Science Advisory Board. In terms of training, Jeanne has a bachelor's degree in chemistry from Northwestern. She then stayed at Northwestern to do a master's in civil and environmental engineering, and then stayed to do a PhD in the same field. And she joined Carnegie Mellon in 1999, and she's remained there ever since. She's won a number of very prestigious awards and honors. I'm just going to highlight a few. In 2013, she was given the Philip L. Dowd Fellowship at Carnegie Mellon. In 2015, she was awarded the Carnegie Science Center Environmental Award. In 2015, she was awarded the American Society of Civil Engineers Margaret S. Peterson Award. And in 2011, she was the National Academy of Engineering Gilbreth Lecturer. She is currently chair of the Carnegie Mellon Faculty Senate, where she is also the co-chair of the search for the new president at Carnegie Mellon. She's a licensed professional engineer in the state of Delaware. Her research is in environmental systems, including the biotransformation of recalcitrant organics. She's drinking water, natural systems, and also she looks at the environmental impacts of energy extraction. So please join me in welcoming Jeanne Vandriesen.
Great, thank you for that generous introduction. I get tired listening to all of those things. I am going to talk to you today specifically about issues around water and energy, the nexus of water and energy, and some of the impacts our choices in energy systems have on our drinking water systems. And of course, it goes without saying, but I'm going to say it anyway, professors don't do a lot of work, graduate students do a lot of work. And this is the work of a number of graduate students from my laboratory, Jess Wilson, Jushin Wang, and Lauren Strauss, who have all graduated, and Kelly Good, Chelsea Kolb, and Adam Cadwaller, who are in my group currently. Kelly and Adam will be graduating this year, so if you're looking for a postdoc, certainly give them a call. Carnegie Mellon is in Pittsburgh. We're at the headwaters of the Ohio River. The Allegheny Basin and the Monongahela Basin meet in Pittsburgh to form the Ohio, which then travels 1,400 kilometers downstream to meet up with the upper Mississippi to form the lower Mississippi. Those of us in the Ohio River Basin like to remind everyone that the Mississippi River really should be called the Ohio River, because the discharge from the Ohio at the point at which the upper Mississippi connects is larger. So we would normally, if it weren't for that straight line down the middle of the country, we would have called that the Ohio River, which then flows all the way down to the Gulf of Mexico. So things that happen here don't stay here. right? Things that happen in Pittsburgh have an effect on most of the middle part of the country. So in my group, we've been focused on anthropogenic bromide emissions, discharges, and their impacts since about 2009. Now, if you know anything about bromide, it's an element, periodic table, kind of benign, used as a tracer for lots of different things, has no human health impacts, except it might make you a little sleepy if you have too much of it. It has no ecotox impacts. Bromide is so incredibly unimportant that you might wonder why we have spent so much time and energy over the past few years looking at it. And the reason for that is that even though bromide has no significant impact in the environment, it is incredibly important in your drinking water plant. Source waters, by which I mean anything out in the environment that we might grab and decide to treat for your drinking water, contain lots of different things. They contain organic matter, they contain inorganic things like iodide, bromide, and nitrogen. All of that source water goes into your drinking water treatment plant where we do coagulation, settling, filtration, and disinfection. Disinfection is incredibly important. Please don't leave today and go home and tell anybody that I told you not to disinfect your water. Okay? Definitely not the take-home message. You must disinfect your water in order to control cholera and dysentery and typhoid and a bunch of other awful things. When you disinfect that water, the reaction with those natural components in the water is to form what we call, not surprisingly, disinfection byproducts, like the four I've shown here, which are trihalomethanes, chloroform, bromoform, and mixed brominated chlorinated compounds. It won't surprise you, especially the chemists in the room, to hear that DBPs are carcinogenic and teratogenic. They cause cancer and birth defects. They're bad for you. It would be ideal if we could disinfect your water and form no DBPs. That is not possible. So we are always balancing the need to control cholera with the need to control cancer, right? Will it make you sick today? Will it make you sick later? That is always an ongoing challenge for us. Bromide makes that challenge much worse. If the source water is elevated in bromide, the DBPs will be elevated in bromide, and there will be more of them. And so brominated DBPs are more toxic and more problematic than chlorinated ones. Increasing the bromide in your source water serves no useful purpose. There's no reason why this would be good for you, and it is, of course, bad for you. There's one clear example, and obviously I've highlighted it here with the bromide in those compounds. You can't get a brominated DBP without bromide, right? Mass balance still works. You will have no bromide in your DBPs if you have no bromide in your source water. In addition to forming brominated DBPs, bromide also increases the rate of formation of DBPs. So you will have more, and it will be more toxic. Where does the bromide come from? Well, again, on periodic table, so it's on planet Earth, right? So there are some natural sources of bromide. It is present in seawater, and so it's present in drinking water sources that are affected by saltwater intrusion. It's present in rainwater, so it's present in runoff. It was widely used in lots of different chemicals. Methyl bromide is a primary example, which we used as a soil fumigant for 100 years. So a lot of soils contain excess amounts of bromide from that. Ethylene bromide, which we used as an anti-knock additive in gasoline after we got rid of lead, we went to ethylene bromide. So it's in lots and lots of things that end up in the world. The two I'm really going to talk about today are the main anthropogenic sources to river water, and those are power plant discharges and oil and gas discharges. First, I want to talk about oil and gas discharges. If you don't know, and you probably do because you're here and some of your professors are studying this, oil and gas takes a lot of water. Hydraulic fracturing of oil and gas wells uses between 1 and 5 million gallons of water per hydraulic frac. So that's a lot of water going down into the well. It similarly and not surprisingly produces a lot of wastewater, much of which is taken to deep well injection sites like these. So almost all of the produced water, and that's the water that's flowing back up out of the well after a hydraulic fracturing activity, is going to deep well injection somewhere in the country, except in Pennsylvania. In Pennsylvania, we thought it was a good idea to take this to conventional treatment plants. So for many, many, many years, long before the shale gas boom in Pennsylvania, conventional oil and gas produced water was taken either to POTWs, publicly owned treatment works, that's the same place everything you flush goes, or CWTs, centralized waste treatment facilities, called brine treatment plants. The most important thing to understand about a brine treatment plant is that it doesn't treat brine. Okay? Brine treatment plants are designed to remove divalent and trivalent ions, some of the organics. A lot of the worst stuff that's in oil and gas produced water is removed at a treatment plant. What is not removed is the clear brine. So what leaves the brine treatment plant, or what leaves the POTW, which is also not designed to remove salt, is a lot of salt. And bromide, being a simple salt, a single ion, is in the effluent. Oil and gas produced water produce somewhere between 100 and 1,000 or maybe 2,000 milligrams per liter bromide. For comparison, these waters have between 50 and 100,000 milligrams per liter of salt. Okay, so the ocean's about 30,000 milligrams per liter salt. The brines in Pennsylvania are about 3 times that, and they contain a significant amount of bromide. Lots of people have studied this, especially in the past 5 years. This is not going to surprise you. If you release bromide to the river, there will be bromide in the river. Got it? Yeah. We've written a lot of papers to show that it is true that when a produced water treatment facility doesn't remove the brine and releases it into the river, that sure enough, the rivers get saltier. Okay? Lots of work. Our work, Duke's work, Penn State's work. You wouldn't think this many people would need to say releasing bromide will lead to high bromide, but we did. Coal utilization. Coal utilization uses a ton of water too, which you probably already knew, for cooling, for makeup water, lots of water going into a coal-fired power plant, and lots of water coming out of a coal-fired power plant. Some of the worst wastewaters coming out of a coal-fired power plant are associated with this source, which is flue gas desulfurization water. Flue gas desulfurization water is water that we used to carry the waste out of the air. So you remember acid rain from like 4th grade science? Bad, right? Acid rain, bad. Sulfur dioxide, nitrogen oxides released into the environment cause acid rain. What do? You put a flue gas desulfurization system on your power plant, takes that sulfur dioxide out of the air, puts it in the water. No problem. This is what we do with all wastes, right? We move them from the air to the water, or the water to the air, or the air to the soil, move stuff around, right? It was a good idea to do that. Unfortunately, it led to the unintended consequence of bromide discharges from these facilities. Bromide has never been regulated in an NPDES permit for a power plant. Occasionally there's a monitoring requirement, but you may discharge to the environment as much bromide as you would like from any of these facilities. And that makes sense, right? I know it sounds crazy because I'm going to tell you why it's a bad idea, but it has no ecotox, it has no human tox, it is not bioaccumulative. There's no reason why anyone would have worried about these bromide discharges. Coal-fired power plants have bromide in them because coal has bromide. Right? Lots of different coals have different amounts of bromide. Engineers are really, really amazing. They discovered that bituminous coal, which has a lot of bromide, if you burn that, you will produce less mercury released to the environment. Do you feel like we're playing whack-a-mole yet? Okay, sulfur dioxide, bad. Okay, I'm getting this bromide. If you have a high bromide coal, you will release less mercury. So what should I do to my coal if it doesn't have a lot of bromide in it? Add bromide, sure, of course, right. Bromide is our favorite way of doing mercury control. When the MATS rule comes online, many, many utilities will decide to add bromide in order to control mercury, which it does really, really well. Bromide has another really nice benefit, and that's similar to chloride or chlorine, and it kills things. Cooling towers are very hot, kind of like hot tubs. In your swimming pool, you probably use chlorine. In your hot tub, you probably use bromine. It's more stable in hot temperatures. So cooling towers use bromine as well. So there are lots of places within the power plant that this bromide's coming from. I basically already said this, and that is that if you do nothing, your bromine will be released out of the stack. Any bromine you add, any bromine that was in the coal will go up the stack. If, however, you deploy wet flue gas desulfurization, it will end up in the river. At about 50 to 100 milligrams per liter of bromide is coming out of a wet flue gas desulfurization system when it's running. Okay, how bad is it? How much bromide are we talking about in these wastewaters? So this is a log plot showing you different sources of bromide. It's in milligrams per liter. That's going to be important because you're going to see some later that are in micrograms per liter. So if you look at the oil and gas produced water, up there it's somewhere in the hundreds to thousands of milligrams per liter. I broke out the Marcellus wastewater and the conventional just so you could know. Pennsylvania water, wastewater from oil and gas development, is high in bromide. It does not matter whether it's shale or not. It's all the same. It's high in bromide. I also showed the brine treatment plants there, just to remind you that they didn't remove any bromide. So that is the effluent from the brine treatment plants, and it looks pretty much just the same as what went in. Right? And then the coal, I'm not going to talk too much about coal mine discharges or abandoned mine discharges. They look a lot like groundwater. But coal-fired power plants, as I mentioned already, 50 to 100 milligrams per liter. How bad is that? How much enriched is that? Well, if we look at your drinking water plants, and EPA looked at these in 97 and 98, they looked at every drinking water plant in the US serving more than 100,000 people. They asked them all to measure the bromide at their intake for 18 months and report the results. US drinking water supplies are typically under 100 micrograms per liter or 0.1 milligram per liter. Right? So we're talking about a significant elevation in both of these waters. And this is an important number to remember. The median value in drinking water intakes in the US was 30 micrograms per liter. Okay? At 30 micrograms per liter, some utilities were having difficulty with those DBPs, but most were not. Most utilities in 97, 98 who were having trouble with DBPs were not having trouble with brominated ones, because the bromide at their intake was only 30 micrograms per liter. Okay, the wastewaters have bromide in them. Okay. How's that going to get to a drinking water plant? We surely control the discharge of things that are going to affect our drinking water, right? So how would I take any of those wastewaters and actually see them showing up in a drinking water plant? Well, to look at that, we looked specifically at one of our two basins in the headwaters, so the Allegheny Basin. This is now the upper of those two basins that meet to form the Ohio. The Allegheny Basin has 4 facilities that treat brine wastewater. In 2011, after numerous reports of this problem, PADEP asked those brine treatment plants and the shale gas providers that were using them to stop using these for shale gas produced water. So now they only take conventional produced water, and it isn't any different. Right? But we did at least stop sending the huge, significantly higher volumes we were sending with shale gas water. But these are those 4 locations, and this, out of one of the Duke papers, is what that discharge looks like. We also have some coal-fired power plants in the basin, as you could imagine, since there's a lot of coal in western PA and since we need to generate electricity. We have 4 large coal-fired power plants that are shown in blue up here that use wet flue gas desulfurization. We also have 5 smaller power plants that use dry flue gas desulfurization. Dry flue gas desulfurization does not affect bromide, and it is typically used by smaller plants. When we first started seeing these results in a meeting with EPA, they said, we would have told everybody to use dry if you had just told us this was going to be a problem. And I didn't know this was going to be a problem. I don't think anybody knew this was going to be a problem. But yes, if we'd thought about it, if we'd known this was going to be a problem, we could have said flue gas desulfurization all has to be done with a dry form, and then this problem would go away. However, the power plants that already have wet are not likely to tear it all apart and replace it with dry. It also won't surprise you that there are, just a few drinking water plants in the basin, 59 to be precise. Surface water drinking water plants are very common in large river systems, right? It's a lot of water. It's easily accessible. The Allegheny and the Monongahela are navigationally controlled river, which means we control the pool height. Before they were navigationally controlled, they were kind of crappy water sources because sometimes the water would only be a few feet high in the summer. But now that they're controlled, the pool is always there. And so many cities that would have been on groundwater 100 years ago are on surface water now. Now, there are only 8 plants that are downstream of these discharges. So the other 51 plants have nothing to worry about. And I'm just going to reinforce that because this seems confusing to EPA. EPA seems to think that if you put a pin in the location of the coal-fired power plant and you draw a 5-mile radius around it in all directions, that those would be the affected drinking water plants. And I just want to remind you that water flows downstream. and that drinking water plants that are upstream of discharges are not at risk. Right? But I also want to mention that drinking water plants that are hundreds of miles downstream are not at risk. Right? It's bromide, it's conservative, we use it as a tracer. It's not going anywhere. Right? Those 8 drinking water plants that are downstream have something else in common. They're all really big. So while it's only 8 plants, 14% of the drinking water plants, it's 36% of the people. It's 500,000 people who live downstream of these discharges in this basin. We were particularly interested in looking what's happening at the furthest downstream drinking water plant, which is the supply for the city of Pittsburgh. So looking at that furthest downstream plant, we asked ourselves, can you tell how much bromide is going to be at their intake? And can you tell where it's coming from? Now here you get into one of the major challenges, although thank goodness the math is really easy. One of the major challenges is that we put bromide out into a river, and the river is not static. The river has water in it. It has a lot of water in it in March, right after the snow melt, and not very much water in it in July, when it doesn't rain every day in Pittsburgh. July is a really nice time to visit, because it doesn't rain every day. What that means is for this particular location, while I might have a baseline amount of bromide that's coming from all the non-anthropogenic sources that stays the same all year long, the amount of bromide as a concentration that I'm getting from the other sources, from the oil and gas produced water and from the power plants, varies across the year. So this is the bromide concentration predicted at the intake to that drinking water plant from these 3 sources. So in March, when the flow is pretty high, the combined amount is about 50 micrograms per liter. Remember what the median US one was? 30. Right? So in the best conditions in this river, I'm at 22 with no other impacts, but with these 2 sources that are prevalent in this region, I'm at about 50. In July, August, and September, September is a really nice time to visit. In September, it's really dry. And so the lower flow in the river offers less dilution. One of the incredibly fascinating things to me about the bromide work, it is the only time in my professional career that dilution was the solution to pollution. It really, really is. At the drinking water plant, 50 might not be a problem, but 120 is. Right? So I really do have to worry in August that I'm going to be seeing significantly elevated DBPs from this amount. Now, this is a model. This is a model based on the amount of bromide in coal that's being burned at those particular power plants, being discharged into the river, and the amount of bromide in that oil and gas produced water, and a background number that took us considerable effort to figure out. Now, we were lucky in this case in developing this model that that particular drinking water intake at PWSA knows they have a bromide problem. They've had a bromide problem for several years now. They've been measuring the bromide at the intake every day. So I can happily tell you that the model's pretty good. Okay. For those of you who are students in the field, in the audience, you don't get this much data. Sorry, doesn't happen. The ability to really look at the monthly amounts of coal purchased at these utilities, the type of coal they were buying, looking at all of the discharges from the oil and gas wastewater, and then having a friendly neighborhood water treatment plant that just happened to be doing daily measurements for the value that you wanted to predict. So we're pretty confident that this model is solid in terms of what it tells us for the loads of bromide going into this river and how they are diluted over time. Okay. Now, at this point, I often get people who say, wow, Pittsburgh, I guess I better not drink the water there. But, you know, maybe it's just Pittsburgh. I hear this a lot from people in eastern Pennsylvania. You know, western Pennsylvania, you got oil, gas, coal. We're really sorry, right? But it's, yeah, it's going to be terrible there. But maybe we're the only place that has to worry about this, right? Yeah, no. So here's the shale in the U.S. You're probably familiar with this picture, right? If there's shale under you, hydraulic fracturing is coming to a city near you. This is an incredible wealth of natural gas. We are likely to exploit it. Here are the coal-fired power plants in the U.S. Yeah, you know, we burn a lot of coal. I know we like to say that we're moving towards renewables. Are we at 5% yet? 6% maybe renewables in the US electric grid? We burn a lot of coal. I didn't mention on that last slide that the concentration changes on the coal, those were totally driven by flow. The power plants in our basin, and in many places where they're coal, they burn the same amount of coal all year long. These are base load plants. These are not peaking plants. This is just the electricity you use all the time, right? They don't go up in the summer. Gas plants peak. Coal plants just run base load. So every one of these triangles you see that is blue is a coal-fired power plant with wet flue gas desulfurization. Every one of them is currently discharging bromide to your source waters. Many of them are going to be discharging a lot more bromide soon because they're going to be trying to comply with MATS. And so I want to briefly tell you a little bit about the two regulatory drivers in this space. One is MATS and one is the ELGs. MATS, the Mercury Air Toxins Standard. MATS, for those of you who study policy, has been a long time coming, right? We had the Mercury Air Quality Rule. We had 3 or 4 versions of this have been to the Supreme Court before we finally got to, yes, indeed, mercury's bad for people and power plants should stop putting it into the environment. Okay? The MATS rule requires power plants to control the amount of mercury emissions. Now, I want to be really clear about this. When you apply a mercury control technology, you're not taking the mercury out of the air and putting it into the water. That is not what we do. Okay? We take it out of the air, we put it into solid waste. However, if you apply bromide in order to enhance the removal of mercury, which has to do with the redox conditions in the boiler, what the bromine does to the redox state for the mercury, making it easier to capture. If you do that, the mercury goes in the dry waste stream, and the bromine goes in the wet waste stream with the FGDs. So we expect that bromide addition will be used extensively for mercury control. The ELGs. Last fall, 2 falls ago, fall of 2015, we updated the effluent limit guidelines for coal-fired power plants. We had not changed them in 40 years. It was really good that we changed them. However, now we're going to not change them. So this effluent limit guideline rule was just recently, as of September of this year, the compliance dates for this were postponed. The EPA is currently taking another look at the effluent limit guideline rule. Now, from my standpoint, from bromide, doesn't make any difference to me. They didn't regulate it in the other one. It was not regulated in the first effluent limit guidelines. It was not regulated in the ones in 2015. It's unlikely to be regulated in the new ones, although I keep sending comments, right, that bromide ought to be regulated. So bromide's not directly included. However, the ELGs have this really interesting language in them. Just really curious. Depending on the site-specific conditions and applicable state water quality standards, pause for me to say there are no water quality standards anywhere in the United States for bromide. None. Why would there be? It's not an ecotox risk. Not anything. It may be appropriate for permitting authorities to establish water quality-based effluent limitations on bromide, especially where steam electric power plants are located upstream of drinking water intakes. There's another little phrase in there somewhere about regulators collaborating. I just want to pause there for you to imagine. Regulators collaborating on the discharge permits, the regulators of the drinking water industry and the regulators of the power plant industry, collaborating to determine an appropriate discharge limit at the power plant. That would be amazing. I can't exactly understand how that would work because the Clean Water Act is over here. Those people are in a different building at EPA, and the Safe Drinking Water Act is over here, and I think they've met. But sometimes I'm at meetings where I invite them both and I'm introducing them to each other. So those two regulatory worlds live very, very separately. Okay? To really be able to manage this bromide risk is going to be challenging. And I don't have a solution for that, but I did want to show you what will happen if we don't, because that's always an interesting thing to look at. So at this same intake location at Pittsburgh Water and Sewer Authority, because I have this model that lets me look at the loads and the effect of the loads on the dilution and then the bromide concentration, I can play that what-if game, right? So I can look at what if these power plants chose to add bromide. So the first thing I can tell you is that the bromide load from an individual power plant approximately triples when they add bromide for mercury control. I can tell you what that will look like for the concentration. So here's August only. I'm showing you just August because it's one of our driest months, so it's one of our worst case. This is the median bromide concentration at that intake. So about 38 of that is from wet FGD, about 60 or 70 from the oil and gas produced waters, and 22 from natural background. Okay, so what if? What if the power plants, all 4 of them, chose to add enough bromide to control their mercury? Well, then my bromide would look like this. Then my August bromide concentration would be more like 220, and 116 of it would be from those power plants. Okay. That is not something your drinking water utility can handle. What was the median again? 30. Yeah, 30 we like. 30 is good. Okay. 125 is bad. 200, and you are into needing to make significant process changes in the drinking water system in order to control the DBPs and prevent negative human health outcomes. Now, maybe it's really important to control mercury. Maybe that's important enough to us that we make a different decision. Maybe we say, yes, okay, mercury control, really important. Go ahead and put the bromide in. Maybe the oil and gas producers should stop discharging to the rivers. So if we take out the oil and gas produced discharges and allow the power plants to add bromide, well, then we're right back, pretty much back where we are now. Not a great place to be, still way above 30, but if my utility is currently able to comply, my drinking water utility is meeting my risk standard, well, maybe this is the decision we make. Right? We decide it's okay to add bromide for mercury control as long as you stop putting oil and gas wastewater in. Of course, it's very important for me to mention that we could also choose to not put any anthropogenic bromide into the environment, and then it would be 22. Right? We're way back down where we would expect to be for a typical river in this region. Okay. Again, it'd probably be a good idea to know whether you have to worry about this beyond the Allegheny Basin. Is this going to affect my utility? So we went just a little bigger. We didn't do the whole United States yet. We'll get to there. We looked just at Pennsylvania, and we looked at all of the drinking water utilities in Pennsylvania, and we looked at all of the power plants in Pennsylvania, and we said, okay, well, some of those drinking water plants aren't even downstream of power plants, so let's look at just those. So 21 intakes in the state of Pennsylvania are downstream of a coal-fired power plant with a wet FGD discharge. That's 22 systems serving 2.5 million people. Remember how EPA did this? Put a pin at the power plant, draw that 5 mile. They said there were 118,000 people in Pennsylvania who would be affected. And therefore, the ELGs did not need to consider this source as a concern. 2.5 million, 118,000, yeah, that's not the same. Right? So there's a significant number of people who will be affected from these bromide discharges. I'm going to show you the loads of those discharges without MATS control. So this is nobody's adding bromide. This is the basic amount of bromide coming out of the coal at those power plants. The 21 drinking water intakes are shown here, and this is the median load predicted. So this is now a mass, kilograms per day, that's coming out. I'm showing it to you by power plants. So one of the things you can see, of course, is that drinking water plant 1 is downstream of only 3 power plants, and drinking water plant 5 is downstream of all 4 power plants. Purple is the Allegheny Basin, orange is the Monongahela. I just love bromide. Ohio is the sum of the Allegheny and the Monongahela, because mass balance is really good, right? So all I do is add bromide. If you add bromide, you just keep adding it. Yes, the river dilutes, and I'll show you the concentrations in a minute, but the loads just keep getting added, right? So the loads in the Ohio are significantly higher than anywhere else. The loads in the Susquehanna are quite low. There's only a couple of power plants there. Okay, well, what happens when those loads get into those rivers? I've said this a couple of times, but here's my slide for it, how dilution works, right? We put the mass in the water, right? And so those loads are then diluted by the flows in the river. Big flow, big load might be fine, right? Big flow at a certain time of year might be okay to dump a lot of bromide in March, right? Also very different for the different rivers. The Susquehanna is a very large river. The Monongahela is a very small river. The way we've looked at that is here the yellow dots are identifying the drinking water intakes. The bars are identifying the bromide loads at the power plants. If I add bromide for mercury control, I'm going to, of course, have these much higher loads. Right? You can't tell from this, though, how big are these rivers? How much dilution am I going to get? So here I'm going to enlarge those little yellow circles to a size that represents the flow. Right? So you can see the Ohio with those really big blocks. Well, right, the flow from the Allegheny and the Monongahela meet. The load meets, but so does the flow. And you can see in the Susquehanna over here on the right, I suppose I should point out those rivers because you don't live in Pennsylvania. The Susquehanna over here on the right, a very high flow river, right? Almost as high as the Ohio. And you can see the Monongahela here, a tiny little flow river. That's a very small river coming together with the Allegheny to form the Ohio. So if I take those loads and put them in those flows, then I can predict the concentration. And just looking at the darkness of those dots, I can tell you that the Monongahela's got a problem. Right? When I look at the Susquehanna, I say, oh yeah, that's not too bad. That's somewhere down here. Under base conditions, it's 5, 10, 15 micrograms per liter of bromide. Even if I add bromide, I'm only in the teens. These are now not the concentration at the intake. These are the contribution at the intake from these power plants. I didn't put background in here. So this is just how much is coming from the power plants. And so in the Mon, we have a problem. Right? We have pretty high concentrations in the Mon from the power plants. Okay, but is it bad enough to worry about your drinking water, right? Cut to the chase here. Yes, there's a lot of bromide out there. Yes, we wrote a bunch of papers on how much bromide is out there. Does it matter? Right? So for the does it matter question, we actually went to the other basin, the most affected basin, the Monongahela. And I wish I could say to you that we got this far in the research, we looked at the Mon and said, oh, that's the one to study. But no, truthfully, we did this Mon study work years ago, long before identifying it as the worst impact, because I was getting calls from the drinking water intakes on the Mon. On the Mon, people were calling me and saying, what is going on with my bromide? Why are my DBPs so high? Where is this bromide coming from? We actually did a really quick study to try to determine if the bromide was an impurity in the chlorine they were using for disinfection. Because there is a small amount of bromine in the chlorine they use. That's laughable compared to all of these significant anthropogenic sources. But we were curious about where this could be coming from. So the first thing I want to show you is what the impact of that bromination is, and then I'll show you the data from the Mon River. So looking at a large data set, this was the information collection rule data from the US, that 97-98 study. We looked at facilities that had low bromide. We compared them to facilities that had moderate, high, and very high. Those bins we just did statistically. Very high was the 90th percentile and above. Low was the 25th percentile and above. Right? We just put it into bins. Compared to the low bromide, if you had very high bromide, your total trihalomethane concentration, that's an indicator of your DBPs, was about 150 times, 150% increase, okay, to the total trihalomethanes. It's the regulated compound. You can see from the scale that it's going to get worse, right? Okay, so we had this increase in how much regulated DBP there was. Then we looked at how brominated are the DBPs. So that was a way of getting at this. Brominated ones are worse. So I want to know how much more of that brominated I might have. And in that case, going from low to very high, it's about a 350% increase in the bromination fraction in the DBPs. And then, of course, we said, well, we should probably look at risk. And from low to very high in risk, we're looking at a 700% increase in the risk of the finished drinking water when the bromide shifts. Now, this is historical data. This is just saying what happens all across the United States when bromide increases. We wanted to specifically look at what happens in the Mon River. And so this is the Monongahela River study. So now that's the southern part of those two basins. The dots on here are drinking water intakes where we took samples. We took samples biweekly for 3 years of the source water and the finished disinfection byproduct water, not the regulated points. Your drinking water is actually regulated where you consume it. We took these samples at the finished water in the plant. DBPs get worse between the plant and your house, but we looked at the plant. Here's the bromide levels quarterly, so taking that biweekly data, rolling it up to quarterly for bromide concentration in the river. Yeah, something was happening in fall and winter of 2010. We had significantly higher bromide in the river. What was happening? Mostly it was dry. Remember that whole concentration dilution thing? Mostly this increase, the load stayed about the same, but we had a drought. And so the concentration of bromide was significantly higher, up in the 100 to 200 microgram per liter range. What happened to the DBPs? Not surprisingly, I'm often saying at DBP conferences, I know, of course, if you add bromide, you get brominated DBPs. There have been at least 100 papers that show exactly this result, although not always in a real person's plant. Those 100 papers are mostly lab papers. Add bromide to the water, disinfect it, you get brominated DBPs. We don't try this experiment on people. Okay, so it's really unusual to see this kind of result in a real drinking water plant where people are consuming this water. But sure enough, in the third and fourth quarter of 2010, we see not only an increase in the DBPs, but more importantly, an increase in bromodichloromethane, dibromochloromethane, and bromoform. So shown here in purple is the bromoform. You can see these little bitty spikes of bromoform within that time period. Drinking water utilities are not used to ever seeing bromoform. To get to 3 bromines, so chloroform to bromoform, we've replaced each of those chlorines, 3 of them with bromines. That takes a long time. That takes a lot of bromide. So it's really unusual to see that bromoform popping up at all. That's the calls I usually get. A utility will call me and say, I have bromoform, what the heck? Right? They're not expected to see that. But the highest risk ones are actually the middle ones, bromodichloromethane and dibromochloromethane, and you shouldn't really be seeing much of those at all. Again, mass balance really does hold. No bromide in the source water, no bromodichloromethane, no dibromochloromethane, and no bromoform. If you don't have bromide, you can't get these. And you can see that in these really, really low concentrations of bromide, that the bulk of the DBPs will be chloroform, which has hardly any cancer risk at all. Let me briefly show you the risks, and I think we're nearly done. So same plot, same colors, except instead of showing you concentrations, I'm showing you risks. And so here, that same third and fourth quarter of 2010, the risk goes from our baseline down here, maybe 5 times 10 to the minus 5th, up to in the range of 1 times 10 to the minus 4th. This is cancer risk only, and these data are from the IRIS cancer registry. Not that great in terms of DBPs. We're not sure these are the right numbers. So I wouldn't stand by the risk numbers, but I would stand by the relative risk. We're seeing a significant increase in risk, even though it's difficult to quantify exactly what those numbers would be. Okay. Oops, a question before I get to the conclusion. Sure. Mm-hmm. Yeah. So again, these are the concentrations leaving the plant. For DBPs in a conventional water distribution system, there are 4 regulated trihalomethanes that are very volatile. They will increase between the plant and your tap. There's almost nowhere that they will be volatilized unless we design it to do that. So in a normal system, THM is going to go up. The other regulated DBPs are haloacetic acids. They're very soluble. They don't volatilize. But they sometimes drop in the distribution system. And I hope this doesn't freak anyone out. They drop because of biodegradation. There are bacteria living in your water. Is that okay? Bacteria living in your water, they're not pathogens, but they do consume some of those DBPs. And so haloacetic acids sometimes go down over time in the distribution system, whereas trihalomethanes always go up. So a couple of things about the fact that they're volatile. That is one of the solutions. Drinking water treatment plants do deploy mixing and aeration in their storage tanks, because the best way to get rid of a pollutant in water is to put it in the air, right, or vice versa. Okay. So you've got that aeration taking place, and those trihalomethanes will be released into the air. There's significant concern when we started doing that if you just look at the straight Henry's law constants, that should remove all the chloroform and leave you with the brominated ones, and that would not be good. And it turns out that that is what you observe if you do, see if I can get this right, if you do certain kinds of bubble aeration, you remove more chloroform than bromoform, just like Henry's law tells you you should. But if you do certain kinds of spray aeration, you remove them in equal amounts. And I am not a good enough physicist to tell you why that interfacial behavior between the air phase and the water phase is not following what I would have predicted from Henry's law. But with spray aeration, you can get them out and get even the brominated ones out. So there are things the drinking water plants can do to remove them, but there isn't much removal by aeration normally. Okay, getting to the conclusions. The conclusions are not that rocket science after this point, right? Power plants with wet FGD and oil and gas produced water discharge bromide to surface water. There's bromide in those wastewaters. We're not removing it. Of course, it's going to end up in our source water. Bromide addition for mercury control is going to be a significant challenge. I've talked with a number of utilities about this, both drinking water utilities and power plant utilities. Bromide addition is not the only choice. It is the cheapest choice if you have certain kinds of existing facilities at your power plant. Okay? Many power plants that have already deployed certain dry treatment technologies are going to prefer activated carbon for mercury removal. And so some power plants are going to go with activated carbon. We have yet to be able to determine in, say, the Energy Information Administration information which power plants are which. Who's going to add bromide, who's going to add bromide, who's going to add activated carbon. That's because in the compliance documents, they have to say they're going to control mercury. They can say by chemical addition, and they don't have to specify the chemical. So it could be an activated carbon process, it could be a bromide process. We just don't know yet for most of them. I assume they know, but we don't know. Increasing source water bromide, increased drinking water risk, even when you meet the standard. And this was probably not all that clear from those diagrams, but you could meet the total trihalomethane standard for your drinking water, even though the risk is significantly higher than it was. And we've looked at that in a number of different facilities where you're able to get into compliance because compliance is total trihalomethane, so you can keep that number low enough. And yet, because you're heavily brominated, the water is riskier. And spatial temporal context matters. Dilution really does solve this problem in a lot of big rivers. If the river is big and there aren't very many power plants, it's probably fine. I live in the Allegheny and the Monongahela, which form the Ohio. 6% of U.S. power is generated in the Ohio River Basin by coal-fired power plants on those rivers. It's going to matter where I am, but it might not matter where you are. Okay, and in acknowledgement, I want to thank all of the various funding agencies and just remind you again that the students do the work. And so this is my current research group and a number of utilities assisted, as well as a number of foundations who provided the support for this work. And with that, I am happy to take any questions.
So I'm sure you've thought that one potential compromise is to not do the mercury removal when the flow is low. So how does that impact overall mercury emissions if you set some threshold of like 100 units where you're not going to do the mercury removal? Is it a big difference with the mercury removal?
So actually, we didn't look at that. We did look at what if you just don't discharge the wet FGD wastewater some time of the year, right? So total wastewater flows from power plants are large, but FGD flows are relatively low. Under the current regulatory realm, wet FGD discharges can be mixed with other wastewaters before discharge. So they often go into the settling pond for ash, and then it's the ash pond wastewater that is discharged, and that's discharged continuously. So it would be difficult for them to say, you know, it's July, run wet FGD, add bromide for mercury control, but hold that wastewater. The new ELGs required the utilities to separate those waste streams and to specifically treat the wet FGD wastewater, not for bromide, but for a variety of heavy metals. So under the new regulatory realm, we thought it would be relatively easy to make a decision to hold the wet FGD wastewater and just discharge it at certain times. The other reason we looked at that is in our region, in western Pennsylvania, the coal mine discharges are pretty salty too. And in July, a couple of years ago, July 2009, we were seeing salt concentrations in the main river that were about 750 milligrams per liter of salt in the river. And the drinking water standard for salt is 500 milligrams per liter. It's only a secondary standard. It's just the water tastes awful. But there was concern because we'd gotten to that 750 number, and there wasn't anything you could do about it at the drinking water plants. So the mines actually put together a model of the system, and now they control their discharges. These are the large underground coal mines, such that we never get anywhere near that. We stay sort of at 450 all the time. They do that by storing the water. They're moving it around in the mine pools. So you're working one part of the mine, and you need that to be dry, obviously, so you can mine it, and you move that water into different places at different times. So we knew that in our region, utilities were already aware of this possibility of controlling discharges at certain times to take advantage of dilution.
How does the volume of water associated with coal treatment compare with the volume of wastewater produced during sort of the peak of shale gas development in Pennsylvania?
So two pieces of coal, right? The volume of water coming from the coal mine dewatering dwarfs everything. The value of water, the amount of water at the coal-fired power plant, if you separate out the fact that a number of these plants still do once through cooling, so separate out the cooling water, the discharge volumes from the coal-fired power plants are, across the region, higher than the oil and gas produced water discharges from those CWTs. But most of the produced water from oil and gas was not going to the CWTs. Most of it was going to deep well injection. So within the basin, the coal-fired power plant flows were higher than the CWT flows. But the total amount of shale wastewater was much, much higher.
I was wondering, you're pretty close to Ohio. Could you take those bromide-containing coal-fired power plant waste and send them to deep well injection?
Could you do that? Yes, one could, I should say. But coal-fired power plants have NPDES permits, right? So the reason the oil and gas produced water is going to deep well injection is at the well pad, you're not permitted to do anything with it, right? You must move it off site. So the transportation costs are even, relatively even, depending on distance, between doing a discharge into my river after treatment and going to a deep well, right? I have to put it in a truck one way or the other, right? And transportation costs drive a lot of that cost, right? At a coal-fired power plant, sure, I could take the wet FGD wastewater and put it in a truck and ship it somewhere, but now you've made it hugely expensive because I have an NPDES permit that says I don't even have to treat it, right? I don't have to remove, right now, under the ELGs that exist, the ones we wrote in 1980, we don't have to remove selenium, arsenic. I mean, there are no requirements for metals removal, let alone bromide and sulfate. So because the discharge permits are really lenient, there would be no driver for my wanting to do that, right? The one thing I will say about the power plants, and this is some work of a colleague of mine, Megan Mauder, also at Carnegie Mellon, she's been looking at whether the waste heat at the power plant is sufficient to desalinate the flue gas wastewater so that the waste heat's free. You wouldn't have to do this. You wouldn't have to take the energy penalty on the electricity generation of treating the wastewater. You could just use the waste heat. And I believe her work suggests that it does work not for forward osmosis, not for reverse osmosis, but for forward osmosis. You can use waste heat to then desal that. Once you're in that space where it's economically viable to treat the flue gas desulfurization wastewater, then we're just at a policy decision. Do we decide to tell the power plants they have to do it? Right? Sorry, it's because my answers are too long.
Hi, maybe I missed this in your talk, but how would you calculate the drinking water risk from DBPs versus the concentrations? And second question, if I may ask, is that, of course, bromide is conservative once it gets into the water, but is there any way to chemically remove it at the treatment plant? Or is it even harder to remove it once it's methylated or combined to organics? Thank you.
Yeah, so first, how did we do the risk calculation? In a very simple and naive way. We took the concentration of the DBP, we multiplied by the IRIS risk factor, and then added them up and called that the risk. A number of people who've reviewed our papers have told us that that's a terrible way to do it, and we always respond to that reviewer saying, yes, but there isn't any other way to do it, right, to figure out what that might be. The way that EPA does this is to take the total, and they have epidemiological studies that look at that total and the relationship to the negative outcome, which is bladder cancer in this case. Because brominated ones weigh more, and the total is a mass-based, don't even ask why, not molar, but mass-based, that method will capture a little bit of the effect of bromide, but it won't really get at what we're interested in, which is how does the increasing brominated concentration, how does that relate to the risk piece, right? In terms of bromide removal, here's the best way to remove bromide from drinking water. Form DBPs and remove the DBPs. Because if you're going to desalinate at the intake, you're talking about 50, 100 micrograms per liter of bromide, right? I mean, think about what that's going to take. You're going to have to desalinate the whole water, and what's mostly in the water? Calcium, magnesium, iron, right? Like, I don't need every non-target thing. All my energy for desalination is going to be for the non-target elements, right? I can't differentially remove bromide. We're working on it, and I'm retiring as soon as we figure it out. But that right now isn't possible, so that desalination piece would be hugely expensive at the drinking water plant. Less expensive at the power plant because concentration is higher, right? It's always cheaper to remove something where it's at a higher concentration than it would be at low. So in the drinking water plant, nobody removes bromide in the source water. But many people do work on ways I can remove the brominated DBPs once I've formed them. I know we're out of time.
So I know there are a few other hands, but there's a class in here, so we're going to have to head out. I do want us to thank Jeanne for a really interesting Okay.
Okay.
spiels and then
Yeah.
my conceptual model first? Because we'll probably run out of time after that.
No, we're not going to run out of time. We're going to keep it pretty brief. I think we should ask them to see what they take away from complex adaptive management before we get to our examples.
Okay.
It's like what they're on, then come back to them, right? And maybe we'll tell them what they're gonna do. I just left my pointer back down in my office.
You want me? I mean, I gotta go down for mine.
You do?
It's not a big deal.
It's 101. Should I just run and get it?
Yeah. A minute. Take a minute.
Yeah, this is the. Yeah, I was gonna say it's the class plan. So. He doesn't like Max. Something like that. Okay, so we're gonna break the class up into like different sort of sections today, where you get to do some talking, we get to do some talking, and we get to step through. But before we begin, there's more people coming in. Let's give them a second. Okay, I was just saying that we're going to break the class up into different sections today. So we want you to kind of, at the end of this class, we want you to come up with a conceptual diagram of what complex adaptive systems mean if you were talking to environmental management. Okay, but before we get there, we want to give you some examples. We want to step through the ideas in the papers, get your thoughts on the papers, and just have you define, or how you define various things. So first of all, what did you think of the papers?